Hello class, so this is our last topic for this semester for chemical reaction engineering, and this is the design of recycle flow reactors. So as mentioned, our last two sets of topics were already divided as part of your culminating requirement. So for the design of recycle flow reactors, we have this particular illustration to use. So we have a PFR here in which a part of the final stream that was remaining unprocessed was recycled back into the reactor feed entrance. So as such, we call it a recycle reactor. So take note of the way we label the streams in this particular recycle reactor. So we have here the molar feed rate. So it's subscript O. This is the volumetric flow rate, V sub O. And this is your conversion, initial conversion, which is in the case of the recycle reactor is assumed to be in this particular illustration 0. Now, I'd like to annotate in this part, this one is our recycle stream. So we will have the volume of this stream labeled as V sub R. R meaning recycle. And we have here the conversion XA1 of the stream, that now the total of these two streams that entered your plug flow reactor. So this is your molar feed rate 1, and this is your conversion 2. Conversion 2 is the conversion inside the reactor, and this is your molar feed rate that is leaving your plug flow reactor. So it's FA2. So we can add here concentration CA1. We can have here CA2. If this is CA2, this must be also CA2. And this must also be, in the case of the final stream that leaves our reactor, this would be CA3. And we can label this as V sub 3. Okay. And we have this one as, we can label this as V sub 2. Okay. V is the volume of the plug flow reactor. We have here concentrations. So this is CA2. So this must be CA2 as well. And we have this one as CA3, where actually CA3 is still equal to CA2. Okay. In the feed entrance, we have here, we can write here V1. Okay, the total stream that is being processed by your reactor. So somewhere along here, you have this node here. We'll have this node labeled as 1. And that is the point where this particular stream, original stream, mixes with the recycle stream. So this is our node 1, and this is our node 2. So when we perform material balance, we make material balance on node 1, node 2, and even on the reactor itself. So we can also do material balance on the reactor itself. So that's it. This is how we this is CA2, so this is also CA2. Okay, so we have here molar feed rate FA2. This is we can have this one as XA2 as well. B3, this is XA2, and that's it. So we have the conversion here as XA2. So this is also XA2. This is also XA2. Okay, now we will go back to our slide. And by the way, this is our slide. Okay, for forgetting, I thought this is our board where we write our solution. So this is how we properly label our recycle reactor. So actually, the numbering here and the labeling depends on you, as long as you properly label the streams and you properly do your material balance based on these two nodes and based on this particular reactor. So this one is using a PFR as your recycle reactor. Okay, so let me clear the markings. So when we speak of the recycle reactor, there is this what we call recycle ratio, and this R appears in the performance equations that were readily derived for us by Levenspiel. So what is this recycle ratio? That's the volume of the fluid returned to the reactor entrance divided by the volume of the fluid leaving the system. So how much of the volume that should be leaving the system was returned back into the reactor feed entrance. So the ratio of that to the original, to the final volume that was dispensed by the system is your recycle ratio. Now, if you don't have volumes here to determine the recycle ratio, we can use the XA1 and the XAF. So your XAF, the XAF here is the XA2 in our illustration. So this XA2 is also XAF, the final degree of conversion, or the degree of conversion of the final stream that leaves your reactor in relation to the XA1. So the XA1 is this one. Okay, the conversion, the degree of the conversion of the total stream process at the entrance of the, of the reactor. Okay, so that's your R expressed in terms of these two. Now, for any system, it may be a constant density system or not, because this is for any epsilon A. So meaning this will work whether your epsilon A is 0 or not equal to 0. You can use this particular formula in determining whatever the problem requires. So you have here the V over the FAO is equal to the product of an integral expression and this quantity R plus 1. Okay, and you have the limit of the integration here. The lower limit is R over R plus 1 times XAF. The final limit is XAF. If the fractional conversion, or rather the expansion, is 0, expansion factor is 0, this is your formula to use. Okay, this one would be okay whether your epsilon is not 0 or not. Both of these formulas are taken from Levenspiel. Now, for a first order and a second order reaction for a liquid phase reaction, a constant density system, these are the ready-made formula that you can use, which has the presence of the recycle ratio. Okay, and we have this particular sample problem. That way we will know how to process a problem in which a part of the final steam that would have been dispensed by the reactor is recycled back into the recycle entrance. Okay, a reaction typically represented by A being converted to B is to be conducted in a constantly stirred tank reactor. The reaction is first order with the established rate R equal to 2 Ca. Now, the unit are pound moles per cubic feet per hour. The feed is 100 cubic feet per hour at the concentration of 1 pound mole per cubic feet. The product removed contains 50 pound moles per hour of unreacted A at steady condition. Now, there are two things that are required in this problem. First one is the reactor volume in cubic feet, and the second, the recycle rate in cubic feet per hour if the hold-up time is 15 minutes, or the residence time, the time your fluid is to be processed inside the reactor, is 15 minutes. And this one is not a plug flow reactor, and this is a constantly stirred tank reactor. However, the principle of material balance would still be the same if we have a plug flow reactor, the one that was given to you in the illustration, or a constantly stirred tank reactor. So let's go to our board to illustrate how this particular problem is to be solved. Okay, so let's write our given. Let's say for this reactor, we will have this as node 1, and this is our node 2. So for the problem that we just read, we have the initial volumetric flow rate. So I'll write it here. H is equal to 100 cubic feet per hour. And then we have an initial concentration of 1 pound mole per cubic feet. And then, just like what was illustrated in the plug flow reactor, we can have the FA1 here. We can have the CA1 here, and the very important V1. So VO, VR, V1. Now in our node 2, we have the FE2 here, we have the V2 here, and we have the CA2 here. And we have, if this is CA2, then this must be CA2 as well, okay? And this must be CA2 as well. Concentration will just be the same. And we have, it says in the problem that 50 pound mole per hour is unreacted. So then that must be the final molar feed rate here, leaving the reactor. So that would be 50 pound mole per hour. Okay, 50 pound moles per hour of unreacted A at steady state. So it's, let me see if we have missed anything. So our reaction, write the reaction is A being converted to B. And your rate is equal to 2 Ca, pound mole per cubic feet per hour. I already wrote the 100 cubic feet per hour here, and the initial concentration, and the 50 pound moles remaining unreacted. Okay, so far that's it. We are asked to determine, so we are asked to, I'll just write the required here, so we'll have everything in one page. So we are required two things: the reactor volume, so letter A would be the V, and letter B will be the recycle rate in cubic feet per hour. So that would be your VR. Okay, so since our unit here in volume is cubic feet and the time unit is hour, so there's no need for us to specify the unit. So these are the two required information. Now let's go to the next slide for our, or another next sheet for our solution. Okay, so we will start with letter A. So letter A requires the volume of the reactor. And when we speak of the volume of the reactor, we know that if it's related to space-time, that would be the volumetric flow rate times the space-time. Now, for us to be able to solve for V, we need to know the V1. So if we go back to our illustration, the V1 is the total volumetric flow rate that enters our mixed flow reactor, the sum already of V sub O and the recycled stream. That's the V sub R. So we need to know that. That way, with the given holding time or residence time, and even the space-time in this case, we'll be able to solve for the volume of the reactor. And since we don't know V1, we will label this as equation 1. Then we can use, or we can do material balance on point 1. Or I'll change the color of this because we labeled that as red. So if we do material balance on 1, that would be molar feed rate, FAO, plus FAR. Your FAR is the feed rate of the recycle stream. So we'll have it FAR here. So FAO in here. So FAO plus FAR would be FA1. Now, in terms of volumetric flow rates and initial concentration, this can be written as V sub O CaO plus V sub R Ca2. Then this would be equal to V sub 1 Ca1. Okay. Now we know that our Ca2 is equal to Ca3. And the Ca3 is equal to the volumetric flow rate of the final stream, or rather molar feed flow rate of the final stream divided by the volumetric flow rate. If we will substitute values, this would be equal to 50 over 100. Our Fa3 is the unreacted moles of A leaving the mixed flow reactor. We divided by the volumetric flow rate. Now, where did we get the 100? If we go back to our drawing, the VO is 100 cubic feet per minute. Automatic, we can say that this VA3 would also be equal to VO. Because if we do material balance here, cut through here, VO should be equal to VA3. Or VA3 should be equal to VO. So we use the value of 100 cubic feet per hour for our V3. So this gives us a concentration, a final concentration Ca3 and Ca2 value equal to, this is 0.5 pound mole per cubic feet. Okay. Now if we go back to our here to our equation, let's see what we know and what we still do not know. So we know this, we know this we still do not know. The recycle stream volumetric flow rate Ca2 we just determined. V1 we don't know also, because that's the reason why we set up this equation, because we need the V1 from this equation to be substituted here. Then Ca1 also, this one is not known yet, the Ca1. Now, since not yet not all the informations that we need are in here, we can label this temporarily as our equation 2. So this is our equation 1 and this is our equation 2. So we can do another material balance. So as I have mentioned at the start of the topic, you can do material balance on any of the nodes, or you can do material balance on the reactor itself. On the MFR. Now, if you do material balance on the MFR, Ca1 should be equal to Ca2 plus the amount that disappeared due to the reaction. Okay, let me illustrate why is it Ca1 equal to Ca2 plus the amount that disappeared due to the reaction. In your reactor, you have Ca1 as the concentration of the final feed that is being introduced to your MFR. And Ca2 is the unreacted part of your feed. So if you do material balance, the initial concentration should be equal to the part that was left unreacted and to the part that has reacted due to the reaction. So that is why you have this. The initial concentration is equal to the final concentration plus the part that disappeared due to the reaction. So this is how you set up your material balance for your reactor. Now, in the case of Ca2, we already determined it to be 0.5, so I will place it here. And in the case of Ra, or your rate, that is actually given to be 2 Ca, and your Ca is 0.5. Now, what is that Ca, by the way? So this rate law is Kca. Now, you have to specify what's this Ca. So that Ca is the Ca that remains unreacted in your reactor, and that's your Ca2. So that is why you have 0.5. As for the tau, the space-time, that would also be the holding time because it was not mentioned in the problem that you have a gas phase reaction. Okay, to be certain, we'll go back to our slide. So A to B is to be conducted in a constantly stirred tank reaction. The reaction is first order with an established rate. Okay, there was no mention that you are dealing with a gas phase reaction. And also one thing that tells you that it's okay to assume that this is liquid phase. It's because your reactor is a mixed flow reactor. Most of the gaseous reactions are carried out in plug flow reactor. So let's go back to our sheet. So it's okay to assume that this one has an epsilon equal to 0, or this is a liquid phase reaction. So your holding time, your residence time, and your space time would all be the same if you have a constant density system. So the problem said that it's, let me check. We haven't written it here. So if we go back to our slide again, here the hold up time is 15 minutes. And our time is in hours. So there's a need for us to convert from minutes to hours. So let's go back to our board. And you have to divide this 15 minutes by 60 to have an agreement to the units that we are using. So in here, we can already determine Ca1. And our Ca1 is 0.75 pound mole per cubic feet. So the Ca1 that we don't know here, now we know already. So we have already Ca1. Now the remaining unknown is V1 and Vr. For us to know the V1, we need to know the Vr. So if we do material balance for the entire recycle reactor in terms of the volume of fluids in and out of our system, we'll have this. So you have VO and you have VA3. And we know they are said to be equal because if we cut here, they should be equal. Now, if we make a balance of the volumetric flow rates here in 1, this would be it. So VO plus VR should be equal to V1. VO plus VR should be equal to V1. So we'll do that in our next slide. So, but from 1, VO, the initial volumetric flow rate plus the recycled stream volumetric flow rate should be equal to V1. We will get here an expression of VR in terms of V1. So that would be V1 minus VO, or that would be V1 minus 100. That way, we will have an expression to substitute for VR in equation 2. So this is now equation 3. So this is equation 3. So if we substitute 3 to 2, So what would be the resulting expression? So our VO is 100. Our CaO is 1. And we have for the VR, this one, the V1 minus 100. And the concentration Ca2 is zero point 0.5. So where am I getting all this? We have set up the equation already, and I am substituting it there. Then V1, Ca1. So we have V1, which is still unknown, and the Ca1, which is 0.75. So from this equation, you are left with one unknown, which is V1, which we need for the volume of the reactor. So V1 is equal to 200 cubic feet per hour. Now, knowing V1, we substitute V1 to 1. So we have the volume of the reactor is equal to V1 times the tau, or that should be 200 cubic feet per hour times, again, the holding time, the space time, and the residence time. Oh, sorry, this is over 60 because that's in minutes. So we divide by 60. This is already in hours. So the volume of our mixed flow reactor is 50 cubic feet. This is our answer for letter A. So this is all for letter A. Okay. Now for letter B, you are asked for the recycle rate. So the recycle rate, V sub R, is equal to V sub 1 minus 100. Okay, where did we get this one? We know that the recycled volumetric flow rate plus the initial volumetric flow rate should be equal to the volumetric flow rate, the final volumetric flow rate that is being processed by your MFR. So we know that V1 is already 200. Let me see if we have it here already. That's 200. So that's 200 minus 100. So the volumetric flow rate that is being recycled, or rather the recycle rate, that would be 100 cubic feet per hour. So this is the recycle rate, not the recycle ratio. Okay, if we go back to our slide, so take note, or rather to the required information, it's asking for the recycle rate. I'd like to go back to the slide and point out to you what's the difference between recycle rate and recycle ratio. So if we go back to our slide, what is being asked here is recycle rate in cubic feet per hour. So it's referring to the V sub R, not the recycle ratio. Okay, what is the recycle ratio? Let me clear my drawings. The recycle ratio, if we go back to the main part here, the recycle ratio is this one. The volume of fluid returned to the reactor entrance divided by the volume leaving the system. So let's say, for example, we will use this formula in determining the recycle ratio for the problem that we just solved. So the recycle ratio then for this problem, though it's not required, so we'll just have it here, is equal to V3 divided by volume returned to the recycle entrance. So it should be VR that should be VR divided by V3. What is this V3? That's the final volumetric flow rate leaving our system. So I will show to you in our solution that this is our V3. or BA3, where this one is BR. So the volume returned to the reactor feed entrance divided by the volume that leaves the system. That's our recycle ratio. So it's different than the recycle rate. So if we go back to our slide, rather here, so so it was already erased. Our R then is equal to VR over BA3. Our VR as computed is 100 cubic feet per hour. BA3 is 100 cubic feet per hour also. So our recycle ratio in this case is 1. And notice that it doesn't have any unit. But when we speak of recycle rate, it has a unit of the volumetric flow rate. Okay, so you should be able to distinguish the two, recycle rate and recycle ratio. So that is why I chose this particular sample problem. That way you will have something to differentiate the recycle rate from the recycle ratio. Now there are problems in Levenspiel which allows you to use the formulas that have presented in this set of slides, especially the use of the R. So I'd like you to work out those problems on your own. It will not be given anymore as an added requirement. I know that you have a lot of things to comply because the semester is ending already. So you will only have um, your quiz here to get and quiz in the other topics, okay, which I will be discussing in our GC. This ends the topic on the recycle reactor class. Should you have any questions, never hesitate to ask from me. Some of your classmates, with only very a few I can mention the names, who are clarifying things, and I know that they are really going through and listening to the recording. So I hope everybody would be listening, and I hope also that they are clear enough that you need not anymore ask questions from me. But should there be a need, don't hesitate to ask me. So far, these are the topics that we'll be covering for chemical reaction engineering for this semester. So the rest of the topics, as usual and as practiced, are given as topics for the final culminating requirement. Okay? Uh, I hope you learned something new in this set of slides. So thank you for listening, class, and bye for now.